Hello and welcome to this thing that we do here. Looks like I'm on part I of chapter 6, so I am sorry I am not there yet. Last week I did all the way up through H, even though that's not as much as I assigned, so I got a little bit ahead of myself. I claim to have videos created all the way through H. I hope that's true. All right, let's take a look at 6I. I don't have to be that big or that small. What's happening here is a cart is on a spring, and it looks like it's going to be going in front of a motion sensor. I think that little ghost thing there is a motion sensor, right? For 15 seconds, motion sensor, right? So at time 0, the origin, and that's its origin point. 0 is where the spring is either squished or stretched. So it's got 10 joules of total energy. Calculate the values of M, K, and A. Explain your methods with words as you show calculations. So the energy is equal to 10. So 10 is equal to 1/2 mv squared. What they're doing there is they're showing the work. This they're going to use this to solve for M. So 10 equals 1/2 m. 2, where did the 2 come from? The 2 must be this. Oh, there it is. The velocity, it's a velocity graph. So they're using the velocity graph to get the maximum velocity, which is 2 meters per second. Okay. I thought that was a position graph, and I'm like, oh, that's hard. Okay, no, it's not. Velocity comes right off the graph. Okay. So you can plug 10 equals 1/2 mv squared and solve for m. It's 5 kilograms. And you can get the period off of the graph. Is equal to 2 pi m over k. And so the period can be read off the graph, right? It looks like it happens between 4 and 8, so about 4 seconds. So the period, and it's equal to 4 seconds, so you can solve for k using 4 equals 2 pi square root of 5 over k. Looks like they skipped about 50 steps of algebra. At the maximum amplitude, the mechanical energy is all spring. Therefore, they're using 1/2 ka squared equals 10 joules, and we already figured out k, and we can solve for a. So yeah, they're kind of working through that there, skipping a lot of steps. I'm certainly willing to talk somebody through that a little more if they skip too many steps and you're confused. A dart is shot to the right into the cart. It's the same cart, I guess. At the time when the cart's momentum is greater magnitude than the dart's momentum. In case 1, the dart is shot into the cart at time 12. In case 2, exactly, but it's shot into the cart at time 14. The dart embeds itself into the cart in both cases, and the graphs below show the velocity of the cart as a function of time for both cases. And for 20 to 35 seconds, the dotted line is the graph of the cart's velocity had the dart not been shot. Basically, the faint line is like the original Wonka, Wonka, Wonka. So what we're seeing here is that in case 1, the graph is certainly shifted out of phase, and the amplitudes are a wee bit bigger. It doesn't look like we changed the period much, right? Seems like it's just shifted over a little bit, but the period seems to be about the same. And then for the other case, boom, the amplitude is way less. And I'm not really sure about the period at all. You know, it looks like the period also didn't change. It's just we're out of phase a little bit, a lot of bit. Actually, we're not out of phase that bad, but the amplitude has certainly changed. Explain why the maximum speed and period shown in each case is different from the maximum speed and period had the dart not been shot into the cart. The period is longer, maybe a little bit longer. It doesn't seem like it's the difference distance between bumps. I don't know, man. I'm just feeling like they called that one wrong. The period is the same, but maybe I'm wrong. Maybe you could explain it to me because I don't get it. And so basically, why is the amplitude different? In one case, the dart is going with the cart and it's increasing its speed. And in the other case, the dart must have been going against the cart, decreasing its speed. We're on J. We have a swing in a swing set, a child in a swing set. L is 3 meters. The chains supporting the swing are 3 meters. The child's at point A. Yikes. Really? Way up there? That's crazy. Time equals 0. The child is at point A, perfectly perpendicular to the swing set? Yeah. Okay, don't try this at home, kids. Yeah, it says the angular displacement is negative 90 degrees, and then B, oh my God. Angela uses force sensors. Angela should call an ambulance. And video analysis to make the angular displacement of the chains and the tension in the chains. Wow, good for her. That's amazing. So here's the angular displacement. You can see, and the dashed line shows if the swing is modeled as a simple pendulum with simple harmonic motion and having a period, and that the dashed line and the solid are not aligned. Why? Oh, so why is it out of phase? And it's because the angle is not small. When the angle gets too big, the small angle approximation can be used, and it's not. So basically, if you've seen this, if you get your pendulum out and try to swing it from too bad, it does like a kind of a wonk wonk thing at the beginning until it settles down and starts swinging. Kind of, I don't know, jumps around a little bit at the beginning, right? Pendulums only work as a simple harmonic oscillator if it's a small angle. And so that is what the problem is here. Angela suggests the tension changes 200 when the child swings through 0. The child is neither speeding up nor slowing down. What are correct? The child is not speeding up or slowing down, but it's changing direction. And so that is correct. What is incorrect? The tension is not equal to the weight because the child is not in equilibrium. There's a centripetal force there happening, and so that causes the tension to be greater. Why doesn't the graph above and to the right explain Angela's claim? The tension is 600 at t equals 1 second. The tension on the graph is 600 and 200. All right, and so I'm going to stop sharing.